This is the third part of section A, forces of motion. The third part is called forces of movement. This part is slightly more complex than that which has gone before it. So this time we're going to be looking at F is ma, stopping distance, which are very straightforward, acceleration due to gravity, and we'll look at air resistance and terminal velocity. The questions on this are slightly more difficult in the exam. These are slightly higher level than those which have gone before. So we'll get started with this. Newton's second law, F is ma. So, if we think about the example which went before, and we think about the car with the forces on it, and you've got an unbalanced force, you've got a resultant force, we know that if we have a car, and the car obviously has got a weight and it's got a reaction pushing up, but they're obviously balanced because it's not flying off into the sky or going through the floor. So therefore, it might have a force due to the engine. And that force might act in this direction, and we could say that that might be, say, 10,000 newtons. And therefore, there must be a force acting in the opposite direction. Friction, air resistance, we've got things acting in the opposite direction. And we could say that that equals, say, 4,000 newtons. Now we've clearly got a resultant force. The resultant force is 10,000 take away 4,000. So the resultant force acting on this car is 10,000 take away 4,000, which is 6,000 newtons. So there's a resultant force of 6,000 newtons in that direction. Now Newton's second law says that F equals ma, alright? So if we have a mass of this car, so let's say the mass of the car was to equal say 600, keep the numbers easy, 600 kilograms. So the mass of the car is 600 kilograms. There is a resultant force on the car of 6,000 newtons. So we could say, well, how fast will this car accelerate in that direction? So to look at it, we would say F is ma. The force is 6,000, and that equals 600, which is the mass, times A. So therefore A, divide both sides by 600, so it's 6,000 divided by 600. So if we look, that equals 10 meters per second squared. So this car will accelerate at a rate of 10 meters per second squared in that direction. And now we're going to look at how this can get more difficult as air resistance increases. Okay? So let's think about this example. If we take a mass, and if we think about the mass of 1 kilogram, now hopefully we remember that mass is a measure of the amount of substance that something is made of, and it's irrelevant where it is in the universe. So mass is how much stuff something is made from. But its weight is dependent upon where it is in the universe. So on Earth, the Earth has a gravitational pull which acts on mass. Now on Earth, every mass is attracted to the Earth with a force of 10 newtons. Now on the Moon it would be 1.6 newtons, on Jupiter 20 odd newtons, but on Earth it's 10 newtons, and that's a constant. So any object on Earth is attracted due to the force of gravity. Every 1 kilogram is 10 newtons. Now if we were to do the maths on this and use F as ma, we could say F equals ma. The force is 10, the mass is 1, therefore A is 10 over 1, which is 10 meters per second squared. So the acceleration due to gravity is 10 meters per second squared. And if we were to change this and say, well, let's make this, 2 kilogram mass. Therefore the weight is 20 newtons. Do the maths again. F equals ma, 20 equals 2 times A is 20 divided by 2, which is 10 meters per second squared. So it's irrelevant what the mass is, it will always accelerate at 10 meters per second squared regardless, as long as it's on air. So every object that we ever do now, we can label a force down. As long as we have its mass, we can label a force down and label this mg. Mass times g. And g is the acceleration due to gravity on Earth, and it's always 10 newtons per kilogram, or 10 meters per second squared, okay? Either unit. This becomes more complicated when we think of something falling out the sky, like a parachute. So if we think about somebody jumping out of a plane, let's think about the forces acting on them. So if we take somebody with a mass of, say, 50 kilograms jumps out of a plane. Now, the instant they jump out of the plane, the only force acting on them is their weight, which we know is mg, which we know is 50 times 10, which is 500 newtons. So there's a force acting on this individual of 500 newtons, and that will cause them to accelerate at 10 meters per second squared straight away as soon as they step out of the plane. But of course, once they start to fall, there's going to be another force acting upwards called air resistance, and this force is going to get bigger and bigger and bigger the faster they go. So whilst they initially start to fall at 10 meters per second squared, if we look at this and start to think, well, what happens when this force upwards equals 200 newtons? So when it equals 200 newtons, so the air resistance is getting quite large, we've got 500 down, 200 up, so the resultant force now would be 300 newtons. And because we know F is ma, A is F over m, which is 300 divided by 50, which is 6 meters per second squared. So we can see it's going from 10 meters per second squared to 6 meters per second squared, and as we carry on and carry on and carry on, what we would find is this number here will get bigger, and it will just get bigger and bigger and bigger. So it will go 200, 300, 400, and as this number gets bigger and this arrow gets larger and larger and larger, we notice that the acceleration goes down and down and down from 10 meters per second squared, 9, 8, 7, 6, 5, 4, 3, 2, 1, and eventually this force will be the same. When these forces are the same, 500 newtons down and 500 newtons up, because of air resistance, now there is no resultant force at all. The forces on the parachute are balanced. Now when this happens, a lot of people think that they will suddenly stop in the sky, and obviously that's not going to happen. What happens is they now fall at a constant speed. Because we've learned before, if there is a resultant force on an object, then it will accelerate. However, if the forces on an object are balanced, then it will continue to move in a straight line at a constant speed, or it will remain stationary. Okay? In this case, it was already moving, obviously because it's flying through the sky, so it will continue to move in a straight line at a constant speed. This is called terminal velocity. So the parachuter has reached their terminal velocity, so they won't go any faster. Now if we were to look at this graphically, you would see that with time you could see initially the velocity, this will be velocity, the velocity will just go faster and faster and faster and faster and faster because the acceleration due to gravity. But because the air resistance is getting larger and larger and larger, the rate of acceleration will decrease and decrease and decrease, so it goes up and eventually it will curve. And on a graph, this flat part along the top is the terminal velocity. The forces are balanced, it will no longer accelerate. However, if you then pull a parachute, you are travelling very quickly, but suddenly the force upwards due to the larger air resistance would suddenly be far greater than the weight. That would mean you'd have a resultant force acting upwards. Now, some people mistakenly think the parachute flies up. It does not. That's because of how it's filmed with cameramen. The parachute just simply slows down. So what happens is the velocity will go from a high terminal velocity, it will fall to a new lower terminal velocity based upon the fact that there's a far greater air resistance or surface area, and now you need a far smaller velocity in order for those forces to balance. Okay, so this here would be acceleration. The rate of acceleration slows and slows and slows as air resistance gets bigger. This is terminal velocity where the forces are balanced. You now open your parachute, the forces are no longer balanced, the force up is greater, so you would decelerate rapidly until you reached a new terminal velocity when the forces are balanced due to your much greater surface area. Okay? Now, the last thing that we wanted to cover in this part was stopping distances. Okay, now stopping distances are very straightforward. This is a very simple concept, stopping distances. So if you're driving along in your car and you suddenly need to brake, there are different things which affect how long it takes for your car to stop. Now then, there is something called the thinking distance and the braking distance, and these add together to make what's called the overall stopping distance. So, all it means is this: you're driving along at 20 meters per second and you suddenly need to brake. The time it takes for you to look at the obstacle or whatever it is that's in the road and to think about pressing the brake is your thinking distance. However, once you've pressed the brake, different systems take over, and that's the actual car braking. This is called the braking distance. So your thinking distance plus your braking distance gives you your overall stopping distance. So for example, if you were driving at say 20 meters every second, if it took you half a second to think about braking, to see something and think about braking, if it took you half a second, you'd have driven 10 meters whilst you were processing the information. Then your braking distance would be to do with tyres and things like this. So the examiner is likely to ask you about factors which will affect your thinking distance and braking distance. So factors which will affect it. Thinking distance is obviously things like distractions, alcohol, drugs, tiredness. These are things which affect your mental capability to brake and to think about braking. So alcohol, distractions, mobile phones, all this sort of thing. Things which might stop you from focusing as well on the road, which make which make the time last longer, which makes the distance further. Braking distance is things like the weather, the roads, if the road's slippery, if it's raining, if the brakes aren't very good, if the tyres aren't very good. They are things which affect your braking distance. The only thing which goes into both thinking distance and braking distance is speed. The faster you're going, if it takes you half a second to think, the faster you're going, the further you will travel whilst you're thinking about it. And when you do decide to brake and you actually brake, the faster you're going, the longer it will take you to stop. So speed is in both categories, and your overall stopping distance is your thinking distance plus your braking distance.